Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We have been discussing the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. And today we discuss the solution of a problem from the section Algebra, in particular from group theory. This problem is placed in part B, which is a multiple choice question. It carries 3 marks. The question ID is 704118. This question is suitable for all these examinations. Right. The given question is, in this question, a definition is given. It says, we say that a group G has a property A if every non-trivial homomorphism from G to any group is injective, that is 1 to 1. What's the property A? If every non-trivial homomorphism from G to any group is injective, then we say our group G has a property A. Which of the following groups has the property A? We are given 4 options. Option 1, the cyclic group of order 6. Option 2, the symmetric group S5. Option 3, the alternating group A5. Option 4, the dihedral group with 10 elements. Let's now discuss the solution of the problem in detail. Let G be any group with property A. What do you mean by property A? That is, if phi is any non-trivial homomorphism from G to any group G prime, then phi is injective, means phi is 1 to 1. Non-trivial homomorphism means phi doesn't map all the elements of G to the identity element of G prime. Then it will be a trivial homomorphism. If every element of G is mapped on to the identity element of G prime, then phi is a non-trivial homomorphism. Whenever phi is any non-trivial homomorphism from G to any group G prime, then phi is 1 to 1. That is, if phi is any non-trivial homomorphism from G to any group G prime, then phi is injective, means the kernel of phi is equal to E. The kernel of phi is E. Injectiveness, that is definition for injective. Phi is injective if and only if ker phi is the singleton E. Now here we state a result, a very small result, which will be useful for us now. Result, let G be a group with property A. If n not equal to G is any normal subgroup of G, n is a normal subgroup which is not the whole of G, and G satisfies property A, then N must be the singleton E. Right. Proof. Let N not equal to G be any normal subgroup of G. Then we have the result. The map F from G to the quotient group G by N defined by f of x is equal to the right coset nx. X belongs to G, which we know is a very famous result. Then this function f is a homomorphism and is also a onto homomorphism, and the kernel of f is n. This is well known to us. Now, the kernel of f is n, where n is not equal to G. Therefore, why n not equal to G? N is a proper normal subgroup G. So, ker f is not whole of G. Therefore, f is a non-trivial homomorphism. Thus, we are getting into the property A. Now, since G has property A, the kernel of f must be the singleton E. So, this will imply that n must be the whole of E. Right. So, hence the result. Now, read this result carefully and think of its contrapositive statement. That is, if a group G has a non-trivial normal subgroup, if a group G has a non-trivial normal subgroup, then G does not satisfy the property A. Right? So, if we want to say a given group does not satisfy that property, then show that there is a non-trivial normal subgroup for that. Right? So, with this, we move on to the next slide and discuss the options one after the other. So, these are the options for you. Take the first option, the cyclic group of order 6. In the case of a cyclic groups, every subgroup, if D is a divisor of 6, then there exists a subgroup of order D, unique subgroup of order D. So, for 6, 2 divides 6, 3 divides 6, therefore it has proper subgroups, and in the case of a cyclic group, every subgroup is normal, therefore it has 2 normal subgroups of orders 2 and 3. Clearly, every subgroup of a cyclic group is normal, and the cyclic group of order 6 has non-trivial normal subgroups of orders 2 and 3. Therefore, it does not satisfy the property A. Go to the option 2, the symmetric group S5. For S5, we are certain A5 is a normal subgroup of S5. S5 has a non-trivial normal subgroup A5. Therefore, it does not satisfy the property A. Option 4, the dihedral group with 10 elements, that is D5. Get into the D5, catch hold of all the rotations, then the set of all rotations form a subgroup and it is normal. Recall, the subgroup of rotations in D5 is a normal subgroup of D5. Therefore, it does not satisfy the property A. Right. So, by elimination, you see, the group that satisfies the property A must be in the option 3. That is the alternating group A5. You can eliminate like that. For that matter, we'll also discuss that now. Option 3. The alternating group A5. Right? Now, note that A5 is a simple group. It does not have non-trivial, it has only trivial subgroups which are normal. So, the normal subgroups are, for a simple group, the E and the whole group. It's a simple group. It satisfies the property A since it has no non-trivial normal subgroups. It has no non-trivial normal subgroups, therefore it satisfies the property A. Right. So therefore, the answer to this question is option 3. That is the detailed discussion of the solution of this problem. Now, to attack such a kind of problems, what you need is, you have to accept the definition. What is the definition of the property A? And basing on that, you have to get into the options and discuss. Right? So, I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will definitely meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.